chatting, we can just do that, or you can go ahead and give a talk. Up to you.
Let's see, I will talk in just a couple minutes. Let's see. So we've got, oh wow, okay, we've got Brian and Sydney and Kimberly a little bit. So I'm Dan Cranston at VCU. I'm going to tell you about some joint work with Reem Mahmoud, my PhD student. So I'll tell you what Mohar's conjecture is. Many of you may be seeing list coloring, but I'll tell you about that as well. And so, yeah, so let me just start here. Okay, so this is the definition of a Chem swap. I like pictures better than words. So here are some examples of Chem swaps. So this is a 3 coloring of the Peterson graph. For a long time, we used to have a running joke in my discrete math seminar that every graph theory talk had to have the Peterson graph somewhere. So I just get it out of the way on the very first slide. So what is a Chem swap? So you pick 2 colors, so in this case, blue and orange, and you pick some component of the subgraph induced by those. In this case, that subgraph is connected. So you just pick blue and orange, and then you recolor that component so that everything, the colors there swap. So this is one example of a Chem swap. Here's another one. You could do blue and green, and in this case, the blue-green components subgraph is not connected. There are multiple components, so you just change the colors on one component. If you want to, you could then do another Chem swap on another one of the components. And then sort of the most trivial example of this is you've got some vertex here that's orange, and you do an orange-green swap, but there's no green in the neighborhood, so you just simply recolor the vertex with green. So the big picture of today's talk is we're going to be talking about moving between colorings of a graph via Chem swaps. And you have one coloring and you've got another coloring and you want to know, can I do some sequence of Chem swaps to get there? It's going to be a little bit of a variation on that because we're not going to be interested just in colorings. We'll be interested in list coloring, which I'll tell you about in just a minute. But before I get into more details, I just want to paint a broader landscape. There's this question of reconfiguration. And so given anything, if you could think about a coloring, or you could think about an independent set, or you could think about a dominating set, or you could think about a spanning tree, whatever you like. And you take 2 copies of the thing, and then you want to sort of move from one copy to another copy, where at each step you're taking some small step locally, and then at each intermediate step you want to have another valid instance of the thing. So in our case, one legal step is going to be that you do one Chem swap. You know, it could be, you could be even more constrained, and you could say, instead of a Chem swap, I'm just going to require that you just simply recolor one vertex. That's more constraining. But there's a huge body of work in this area of reconfiguration. And generally, the sorts of questions you ask are, given 2 instances of the thing, can I get from one to the other? Can I get between any pair of them? If so, how long does it take? What's the minimum number of steps? That kind of stuff. Today, we're going to focus on just Chem swaps is our step, and we're going to focus on list colorings, which I'll tell you a bit more about in just a second. But I just kind of want to put it in that bigger context because I think there's a lot of cool problems there. Okay, so Kempe equivalence is just saying you say that two colorings are Kempe equivalent if you can get from one to the other by a sequence of Chem swaps. And this is just a phrase that I made up, K-ergodic, which just means that you can get from any K coloring to any other K coloring by a sequence of Chem swaps. So we saw the Peterson graph, and the Peterson graph is 3-ergodic. And what that means is if you look at all of the 3 colorings of the Peterson graph, you can move between them using Chem swaps and never using more than 3 colors. So here's what turns out to be a really useful lemma, and we'll come back to it later. But basically what it says is if you have a vertex of low degree relative to the number of colors that you're allowed in your coloring, essentially, if you're interested in the question of, is this graph k-ergodic, you can simply delete that vertex. And the idea is you delete the vertex, and now if you can answer the question in the smaller graph, then you get, if the answer is yes, then you get some sequence that moves between two colorings, then you can sort of extend that sequence up to this, this deleted vertex, and you kind of drag it along at each of the steps. And I'll show you more details of a proof of that later. But it's fairly easy to prove. And so then the natural question you get into is, oh, sorry, just a second. So a consequence of that is you can delete one vertex of degree less than k, where you can iterate that. And so if you're D degenerate for some D less than k, then you just keep deleting the low degree vertices. So the question then is, which graphs are sort of barely not k degenerate, right? So this is often done when you're trying to think of interesting questions. Is you think of some sort of simple and elegant argument, and you say, okay, what can we do with that simple and elegant argument? Okay, so in this case, you can do everything that's D degenerate. And then you say, okay, so what's just beyond the edge of what we can do with that very simple argument? And oftentimes it gets a lot harder. You have some simple argument that gets you out to here, and then just to go a little bit further takes a lot more work. And so the natural first question is, what about k-regular graphs, right? If you have any vertex of degree k-1 or less, you can delete it, and then you sort of keep eating away your low degree vertices. But if you don't have any vertices of degree less than k, well, sort of the simplest thing you could have is k-regular. And so Boy and Mohar made this conjecture that every k-regular graph is k-ergodic. So what that's saying is, if you look at any two k colorings of a k-regular graph, you can move from one to another by a sequence of Chem swaps. It's a very natural question. And so Fagali, Johnson, and Pujma came along and they said, yes, the answer is yes. With this one exception, K3 box K2, I'll put this picture up over here. So this is sometimes just called the triangular prism. So I've got 2 3 colorings of the triangular prism, and I cannot move between the one on the top and the one on the bottom by Chem swaps. The intuition is really simple. If you look at, we'll just look at orange and green, say. So there's green, orange, green, orange. If you do a green-orange Chem swap, you'll change the coloring, but you'll never change the underlying independent sets in the coloring, right? You just swap green and orange. Or if you do a blue-green swap, you'll swap the blue and green, but the independent sets will still be the same. So you can sort of never make progress. Whereas if you look at this down here, it has different independent sets. And so you can never move from this guy to this guy. Does that make sense? So I encourage you as we go along to interrupt me if you have questions. It's more fun. I already know this stuff. So if I'm just talking to myself, it's kind of boring. So if there's something that's unclear or you just have a question, just interrupt and say, wait a second, that didn't make sense. So anyway, so FJP proved the 3 regular case, and then Bonamy, Busquet, Fagali, and Johnson. So 2 of these same authors, and then two new in and 1 out. They proved the case when k is at least 4. There are no exceptions there. Okay, so that's kind of the setting. Now, what Reem and I worked on was we want to generalize this conjecture and then ideally generalize the result to the case of list coloring. And if you've seen list coloring before, you kind of know where this is going. And if you haven't, no worries, because I'll tell you all about it on the next slide. Right. So what is a list coloring? So the simplest graph that's a little bit interesting here is the edge, K2. So a list coloring just means that each vertex gets a list of allowable colors that you can use at that vertex when you're trying to color. So for example, this vertex here on the left gets the list 1, 2, and the vertex on the right gets the list 1, 3. Okay, that's a list assignment. And now an L coloring is any proper coloring where everybody gets a color from its list. So for this edge, there's sort of 4 possible things you could try, but you can't use one at both vertices. And the other 3 work, right? So these are the 3 L colorings of K2 for this particular list assignment. You would actually call this a 2 assignment because the list at each vertex has size 2. And we say that 2 L colorings are L equivalent if we can turn one into another via Chem swaps. So this is a very simple example. So the Chem swaps, it turns out, are just going to be simply recoloring a vertex. But if you look up here, if you do a Chem swap, a 1-3 swap here, then the 1 will go away and the 3 comes in. And if you then do a 1-2 swap here, the 2 will go away and a 1 comes in. So there are only 3 colorings from this particular list assignment, and you can move between them all.
So now, here, sorry, question.
No,
so for Chem swaps, you find, a connected component in 2 colors. But when defining connected component, do you specify that the 2 colors also? Oh, no, never mind. That was a really dumb question. I answered it by myself.
It's sort of weird because the thing that you could try, so let me look here. I said, what if I said, okay, so let's do the 1-3 swap here, right? That's okay. And then after that, I can do a 1-2 swap here. But if I were to try and do a 1-2 swap here, right, that would be a natural thing you might try. And that's okay at this vertex, but it's going to fail at this vertex. So what you do is you just simply disallow moves that would either create an illegal coloring, something that's not allowed from the list, or that would create, so if you say, okay, this is the only 1-2 component, but then I do the swap and then I'll have a 1 here and I'll have a 1 here. So you basically only allow things that will create valid coloring. The thing that's a little bit surprising is that you can still say some interesting stuff and develop a little bit of an interesting theory, even under the sense that it feels like list colorings would kind of break Chem swaps and it wouldn't work.
So connected component is, yes, it only uses those colors, but also those colors exist in all lists.
Yeah, I mean, you just say, so so let's see. I was trying to look and see if I have the term. I called it L valid to mean that if I do this Chem swap, I'm going to get another L coloring that comes out. And so I only allow myself to do L valid Chem swaps.
Okay, fair enough.
So G is L swappable means that all L colorings are L equivalent. So in this particular list assignment L, G is L swappable. There's just these 3 L colorings, and it turns out you can't get from the top one to the bottom one directly, but that's okay. You can go through the middle one and you're fine. Okay. K swappable is the next level up. You add an extra level of for all quantification because you're saying it's true for every 2 assignment in this case, right? So I showed you 1-2 assignment, and it turns out that it's true. It actually turns out that for any 2 assignment, this example K2 will be will have all the L colorings being L equivalent. So this graph is 2 swappable. And it turns out, before I get there real quick, turns out that in fact, it's not totally obvious, but it's an easy exercise that if you have a forest is always going to be 2 swappable. And the reason is because you can go by induction because you have leaves. You rip off the leaf, and then the smaller forest is going to be work. And then we'll see this lemma in just a second. But basically, if the leaf would cause problems with what you're trying to do, you can sort of give it a different color so you get it out of the way so it doesn't cause problems. That's the short answer. Okay, but let me show you some examples of things that are not 2 swappable. So these 6 cycles, I have 1, 2, 2, 3, 3, 4, 4, 4, 5, 5, 6, 6, 1 all the way around. And I've given you 2 different L colors, right? Same lists on both, but there's 2 different colorings. And there's nothing you can do from this coloring on the left. There's no valid Kempe swap. And the reason is because, so if you look at like 1, 2, that's going to be a problem, because if you try a 1, 2 swap here, for example, you could do it, but then you'll create a problem here, right? Because this guy can't get recolored with a 1 because there's no 1 there. Okay, and that same sort of trouble persists all the way around. So this coloring is, in a sense, it's frozen. There's nothing you can do to move to another coloring. And you've got these two different frozen colorings. And so this is a 2 assignment L, where you have two colorings that are not 2 equivalent or not L equivalent. Okay, so now with some definitions out of the way, I can tell you our main theorem, which is if G is K regular with K at least 3, G is connected. So this K3 box K2, this is that same triangular prism that we saw. And it turns out that in fact, it's just that one list assignment, something that's essentially isomorphic to the, or that gives the same color to everybody, the same 3 colors to every vertex. You run into the same problems that you saw right down here, right? You could name them something different other than green, orange, and blue, but if they all get the same colors, then you have the same problem. But if it's not that list assignment, then you're going to be okay on this thing. And then we're also just going to steer clear of the clique, because we really want some vertices that are non-adjacent to work with. Okay. So before I go on, any questions? Does the sort of the context make sense? What we're trying to do? Yes.
I have a question.
Yeah, go ahead.
So like in the top left, you said that you can't Kempe chain because there's going to be a problem. Do you know if anyone has studied, or like if it would be weird to look at swapping more than 2 colors?
That is not something we considered. I think, yeah, you're talking about up here. You were saying.
Oh, I definitely meant on the top right, not the top left.
Oh, the top. Oh, you're saying to get from here to here.
Yeah.
Yeah. So it's sort of interesting because in this particular instance, there are only 2 L colorings. The 2 colorings that I showed you are the only 2 that thing has. And you can take a cycle and you can sort of, in the obvious way, you can extend this to arbitrarily long cycles.
Mm-hmm.
And you won't be able to, you won't have any moves except to sort of go to the other coloring, which would require changing arbitrarily many colors. So
so if you allowed yourself like to apply arbitrary permutations to things, then you can do it. I mean, a Kempe swap is just a transposition.
Sure.
Yeah.
But then it sort of becomes a less meaningful statement, I think.
Cool.
Okay.
Thank you.
So let me tell you a little bit about some of the ideas that go into this proof. Right. Oh, right. So this is a beautiful lemma of Las Vernes and Meunier from the early 80s. So basically, I'm going to just give you essentially their same proof, and it works for list coloring as well. They prove something slightly different, but it's basically the same thing. So the idea here is that we want to show that G is K swappable. So we have some K assignment. So every vertex has K colors. And now you've got a vertex with degree less than K, and you want to delete it and show that you can. So here you've got G and you've got some coloring, and you've got some other coloring of G, some L coloring. Sorry, you've got some list assignment L and some L colorings. And you want to get from this one to this one. And so what we're going to do is we'll just delete V and we come down here. And now by assumption, we're able to get between these 2 colorings when they're restricted to G minus V. Okay, we've got some sequence of these steps. And so now what we want to do is we want to extend that. We want to pull it up back to G. So if you look at this vertex V, so let's just say by symmetry that we're doing a 1, 2 swap here. So if V is colored like 3 or 5 or 17, whatever, if it's not involved in 1 and 2, then there's no problem. You just do the Chem swap and V just kind of comes along for the ride. So the only sort of, and the same thing is true actually if V is colored 1 or 2, maybe even 1 with a neighbor colored 2, but it's a different component than the component where you're doing the 1-2 swap, right? That's happening somewhere else in the world and it doesn't really affect you locally, so that's fine. So the interesting thing is when V really is colored 1 and its neighbor is colored 2, it has some neighbor colored 2. Let's just say right now that it's just got one neighbor colored 2. And let's also say that it has, this neighbor has 1 in its list and this guy has 2 in its list, okay? So if that's the case, then we can just simply go ahead and do the 1-2 swap. There's no problem, right? And this is important that none of the other neighbors are colored 2. Because if you had some other neighbor that was colored 2 and you try to do the Kempe swap, then what happens is you may force one of these other components, you may be merging 2 of these 1-2 components into a single one. And then that's causing unintended consequences for the rest of the coloring. So this is fine. So before we go to the possibility of there being more than one neighbor colored 2, what if he's colored 1, but he doesn't have 2 in his list? So now we really still want to do this 1-2 swap. And now here's the beautiful thing. If he doesn't have 2 in his list, then that means he has some other neighbor, some other color here that isn't used on the neighborhood. And so what you can do is you can just do a recoloring of that single vertex and sort of move to the case where he's not colored 1 anymore. Okay. The other sort of really important case is where you've got, let's see, where you've got multiple guys that are colored 2. But then again, it turns out the same thing. If you've got multiple guys that are colored 2, then you're going to have some spare color that doesn't show up on the neighborhood. And so you recolor that vertex V with color, you know, I don't know, teal or something, before you do the 1-2 swap. And so then it doesn't, that's fine. You do the 1-2 swap wherever you want to, but now V is not involved and it doesn't impact anywhere, the coloring anywhere else in the graph. So these are kind of the two ideas is either V just kind of hangs along as a leaf in that component where you're doing your swap, or else if V has at least 2 neighbors that have this colored 2, then you can just color them to something else. You do a 1-3 swap just there, and then after that, you can go ahead and just do your 1-2 swap. And you can kind of think through it. Those are basically the only interesting cases. And so by induction, you're able to drag V along the whole way. Okay. So what do we got here? So if L is a degree assignment, what do we mean by that? We mean that the size of the list is equal to the degree for every vertex. Now, if you've seen list coloring before, sort of the idea of list coloring is it's nicer to prove certain things by induction using list coloring than using coloring. Because when you go, if you delete something and you go to put it back in, you don't necessarily know what's going on the neighbors, but you can just say, okay, each neighbor loses me at most 1 color. And so you can talk about how many colors are available at that vertex. So that was kind of some of the motivation for list coloring. Degreechoosable is saying if everybody has a list of size equal to its degree, then you have a coloring. And this was something that was studied in the late 70s by Erdős, Rubin, and Taylor, and they characterized which graphs are degreechoosable. So if a graph is 2 connected and it's not just an odd cycle or a clique, then it is degreechoosable. And this is sort of one of the first results that it has a very slick proof. And I'll sort of sketch it for you here. The idea is if a graph is degreechoosable and it shows up as an induced subgraph of some connected graph, then that whole graph is degree choosable. Okay, so what does degree choosable mean? It means everybody gets a list of size equal to its degree, right? And then you're always able to find a coloring from those lists, right? So if you think about why can the odd cycle not be degree choosable, it's because the odd cycle is not two colorable, right? Everybody has degree 2, but if you give everybody the list 1, 2, then you can't color the odd cycle. The same with the clique. Everybody has degree delta, but if you give everybody colors 1 through delta, then you can't color the delta plus 1 clique. It turns out that those are the only bad list assignments. Okay, so what are we doing here? So they wanted to prove that if you're not one of these two things and you're too connected, then you're degree choosable. So the idea is really nice. They prove if you have a degree choosable subgraph as an induced subgraph, then you're degree choosable. And then they prove that if you satisfy these hypotheses, then you do in fact have an induced degree choosable subgraph. And the things that they use are really simple. It's just an even length cycle, which it's fairly straightforward to prove that an even length cycle is choosable from lists of size 2. Or an even length cycle with 1 chord. Those are both degree choosable. So what we would like to do, if we go back, so here I want to prove this main theorem. We want to show that G is K swappable. So this K regular, right? So K swappable would be sort of degree swappable, right? So the idea is, again, you want to try to find some induced subgraph that is degree swappable, and then show that if you have a degree swappable subgraph as an induced subgraph, then you yourself will be degree swappable. And then in the case when you're K regular, then that's K swappable. So that's kind of the big picture. So this turns out to be the key lemma. If H is degree swappable, and H is an induced subgraph of a connected graph, then G is degree swappable. And it's this sort of the same thing as the lemma that I proved for you right here, this degeneracy lemma. The idea is the following. So suppose that we have a degree swappable subgraph. Let's just take it out. We'll just delete it. Now everything else is gonna it's going to be degree degenerate. What that means is in every subgraph, you'll have a vertex where there's some vertex where the list is bigger than the degree. And the idea is that you can just sort of work out eroding away from the thing that you just deleted. Because it had a list that was size equal to its degree, and then it lost a neighbor that's in this subgraph that you just deleted. And so it's going to have a list that's bigger than its degree. And you can kind of eat out. And so you can think of that as just this degeneracy lemma. And so then the hard part is just finishing up on the middle. But finishing on the middle, you can do just because by hypothesis, this thing is degree swappable. Okay, so before I go further and tell you more about how we prove that, does that make sense? Just this sort of what I'm sort of sketching this key lemma. If you're degree swappable, right? So what I was doing was I was just saying it for degree choosable. If you've got this thing in the middle and you can finish there, then you can color in and finish. The proof is very similar for degree swappable. It's more complicated, and I won't go into the details, but that's the basic idea. Okay. So what I want to do, I want to compile a big family of degree swappable graphs, and then I want to prove that every K-regular connected graph has some induced subgraph in this family. All right. So let me pause again and just ask for questions. Again, happy to clarify anything before I go on. Pause for Okay. So what are we going to do? We want to prove that a graph is degree swappable. So let's just remember what that means. So a degree assignment means it's a list assignment where everybody gets a list assignment L, where everybody gets a list of size equal to its degree. And degree swappable means that for every one of those list assignments, you can move between all of the valid colorings by a sequence of Chem swaps. So we saw, for example, well, okay, let me just leave that. So how do you prove that a graph is degree swappable? In general, given a list assignment, how do you prove that you can get between all of the colorings? So given a list assignment L, I typically talk about fancy L as being the set of all of the L colorings for that list assignment. So what I'm going to do is we're going to partition this set fancy L up into parts, fancy L1 through fancy LS or something. And what I want is that within each part, I can show that these guys all mix. Okay, and so we'll talk about how we do that in just a second. And then you want to find paths among the parts. So you sort of, so more generally, you can think of, you're trying to prove that everything is one big equivalence class, right? And so what you're trying to do is you find stuff and you say, okay, I can show that all of this stuff is equivalent to each other. And I can show that all of this stuff is equivalent to each other and so on. And then I just pick one representative that can get from L1 to L2. And I can pick one representative that can get from L2 to the next one and so on. And then by transitivity, everything is going to be equivalent to each other. Okay, that's sort of the big plan. So the natural question is, how do you show that a whole bunch of these colorings are equivalent to each other, right? So how do you prove that all L colorings in one of these parts in our picture, I say mix, which means that they're all equivalent to each other by some sequence of Chem swaps. So remember that we're sort of very close to being able to just go by degeneracy. So you can think about the case where you've got a k-regular graph. And if you delete one vertex, after that, everything else is going to be k-degenerate. It's going to be k-1 degenerate, right? As soon as you delete one vertex, then that guy has neighbors that now are missing a vertex, and so you can delete them. And then those guys, now they have new neighbors that are missing them, and so it sort of spreads out, and you can delete the rest of the graph just by this degeneracy argument. So really what we want to do is we just need to find, if you think about the coloring case, if you have, say, a k-regular graph and you're trying to k-color, if you color greedily in towards the middle, it's all fine until you get to the very last vertex, because every vertex has an uncolored neighbor that's sort of closer to the middle, right? And when you get to the very last vertex, you need to do something more inspired. And so one thing you could do is if you have these vertices V and W, and G minus V is connected, and there's some color that's available for V that's not available for W, okay? Now, when you color V with this color alpha, it doesn't use up a color for W, because W wasn't in the list of available colors for, because alpha wasn't in the list of available colors for W. And so as a result, this vertex now effectively has a list that's size larger than its degree, right? And so once you do that, then you can start your degeneracy lemma there, because now effectively its degree has gone down by 1, but its list size hasn't gone down by 1. And so now you can just go repeatedly by this degeneracy lemma. You can do a similar thing if you've got one vertex with two neighbors that have a common color and they're non-adjacent, right? And so if you can think, this is one way that you can think about proving Brooks' theorem, is if you find some vertex with two neighbors that you can color with the same color and they're not adjacent, then you can greedily color in towards that vertex and you effectively save the color for that vertex. So it's the same thing here. As soon as I fix a color alpha on V1 and V2, now W has only lost one color, but it's lost two neighbors. So again, its list now becomes larger than its remaining degree, its effective degree. And so you can go by this, this key degeneracy level. So what that says is all of the colorings that use alpha on V1 and V2, they're all going to mix with each other. And up here, all of the colorings that use alpha on V are going to mix with each other. So it's these types of arguments that you use to say, okay, everything in this set L1, fancy L1, is going to mix. Everything in this set fancy L2 is going to mix, right? And then you have to sort of pick some representative from L1 and some representative from L2 and show that you can get between them. Okay, so now what have we got? So this is sort of an overview, a sketch of how do you prove that a graph is degree swappable? And the idea is we want to collect a big collection of degree swappable graphs, and then we want to prove that every connected k-regular graph contains a degree swappable graph. And then we'll be done. So what are some examples of degree swappable graphs? So I call these chorded barbells. So a barbell, you can sort of think of, you're lifting a barbell, right? Here's the bar here in the middle, and then here are the weights on the two ends, okay? So these are both even length cycles, and then there's some path between them. The path could be degenerate, and they could just have a vertex in common. And then each of these even length cycles may possibly have one chord. So you could have just one of them has one chord, or you could have both of them have a chord, or neither of them have a chord, and then there's some path between them, possibly of length 0. And what we prove is that every graph that's of this type is degree swappable. So that means if these guys all get lists of size 2 here, except these two get lists of size 3, then all of those colorings will mix with each other. Or here, this one would get a list of size 4, this would be 3, these would be 3, 3, and then the other ones would get lists of size 2. So those are, and the way that we prove this is sort of using this approach that I was showing you on the previous slide. Another thing that turns out to be really helpful is just this very specific graph called the 4-wheel. You just take a 4 cycle and then you add a dominating vertex. There's some places where it would be nice to know, for our arguments, it's nice to know that the graph doesn't contain this as an induced subgraph. And so what you can do is you say, well, if it contains it, then we win one way. And then if it doesn't contain it, well, then we can win this other way. Okay, so this is our theorem. So how do we want to prove this? Well, we sort of split into a few cases. We have this low connectivity case and this high connectivity case. So if you have a small vertex cut, S, so it turns out that S is just if you have a vertex cut of size 2 or 3. Turns out that the cut vertex case is easy. So if you have a vertex cut of size 2 or 3, then you can look at each component when you delete this cut set, and it has to look basically like a Galli tree. A Galli tree is where every block is either an odd cycle or a cleat. These play a key role in degree choosability. So if you have a Galley tree, then it's easy to analyze because there's not too many options. But if you don't, then it's with some work you can show that your graph must contain a good barbell or a corded barbell, a good barbell or a good corded barbell. And then these are your degree choosable, your degree swappable subgraphs, which is what you wanted. So if you have one of those, then you're just going to win. So if you don't have that, then your tree has to be basically a Galley tree, but then you have a lot of structure and you're able to see what's going on. If you have a four wheel, then we're just done right away. This is a four wheel. And if you have a four wheel, then again, that's a degree swappable subgraph. So you win because if you have an induced subgraph that's degree swappable, then you are degree swappable. And then the final case is if you're four connected and you have no four wheel, now the fact that you're four connected really gives you a lot more power. Essentially, so if you go back to this picture, I was saying, okay, you could color one vertex here, and then as long as the thing that remains is connected, then you can make progress. You can sort of color in towards W. If you're four connected, then what that tells you is you can pick the colors on any three vertices that you like, and your graph will still be connected. And so you can use this kind of trick, but you get a lot of power because you can specify precisely the colors on three vertices. So that allows us to essentially just explicitly construct the paths between the colors. All right. So let me sum up. What have we done? So Mohar conjectured that all k colorings of a k regular graph are k equivalent. Again, k regular, everybody's degree k. K colorings, you're allowed k colors. And then k equivalent says you can get from one to another by a sequence of Chem swaps, never using more than k colorings. And this is true, except for this one graph, K2 box K3, which is the triangular prism. And our goal in this work was to extend this to list coloring. So this is just a reminder, this is all joint work with Reem. There she is in front of a nice little fence with cool geometry in it. Okay, so what was the definition? L swappable. So you have some list assignment L, and the graph is L swappable if we can move from any L coloring, which is any valid list coloring from that list assignment L, to any other by a sequence of Chem swaps. And at each step along the way, you keep that it is a proper L coloring. The key lemma that kind of drives what we're doing is that if H is degree swappable and some connected graph G has H as an induced subgraph, then G is also degree swappable. And the proof of this is it's similar to this thing about deleting a vertex of degree less than its list size. It's more complicated than that, but it uses the same idea. Oh, I also mentioned this is also useful elsewhere. I had another result that I did recently about list edge coloring and being able to move between list edge colorings of planar graphs. Okay, so our main result is that if G is K regular with K at least 3 and G is connected, then you're K swappable, where as long as you're not this triangular prism and you're just not the cleat. And there are sort of these three cases. One is when you have a small cut set, when you have a cut set of size 2 or 3, each of the components has to mostly look like a Galley tree, or you could get a good barbell or a good ported barbell and you can win that way. If it contains a 4-wheel, then you're just done because we prove explicitly that that is a degree swappable graph. And then if you don't have a 4-wheel and you also don't have a cut set of size 2 or 3, then we can just explicitly say, okay, here's a coloring, here's simply how you move between them. So if you are interested in more, there's about 25 pages of great details and fun pictures. They're on the archive. So let me stop there, and I'll take any questions. Thanks.
Let's just quickly thank Dan. And are there any questions for Dan? I have a quick question, if no one else does.
Yeah, go ahead, Chris.
Okay, so let's just do like normal coloring. Still Chem swaps. But say that I allow you along your journey between two colorings to use some extra colors.
Okay. So
feels like I should be able to get between any pair of colorings if I give you a few extra colors, maybe even two colors. 2 extra colors is good enough. Staying proper. Is this a thing? Like the fewest number of extra colors that I need to have in my universe to get between any 2K colorings via Chem swaps? So my path in between, I can use more colors possibly.
Right. No, I understand the question.
It feels like I should be able to do it with very few colors. Maybe even like 2 extra colors feels almost good enough because I can like swap everything here to a color not used. Then I can swap like the bad pieces to the second color not used and move things. I don't know if this is ever anything that anyone cares about or has looked at.
So the issue, I don't know.
Okay.
I haven't heard it phrased in that terminology. So typically what I've heard is you look at the set of all of the K colorings for some value of K, and typically you compare K to some parameter of the graph, like the degeneracy of the graph or the maximum average degree of the graph, or so I mean, maybe the closest thing would be if you look at, for example, planar graphs, say planar graphs that are triangle free. So these graphs are 3 colorable, and there's a question of you know, can I get from any 4 coloring to any other 4 coloring these things? And one technique that they oftentimes do is they say, okay, I'm not going to really just go from a 4 coloring to a 4 coloring. What I'm actually going to do is I'm going to go from a 4 coloring to some well-chosen 3 coloring, right? Because I know it's a 3 colorable graph. And so then somehow what that does is, by going to this 3 coloring, it sort of is doing a little bit of what you're talking about, of creating this extra color, right? In the sense that what you do is you say, okay, I've got these 2 4 colorings, I pick some 3 coloring in the middle, and I push them both towards that. And as I'm getting close near the end, I know that color 4 isn't supposed to show up anywhere. And so that gives me a little bit of flexibility that I can use it at places where I know it's not going to be appearing in my way because most of the graph is 3 colored or something like that. That's the closest that I know of that actually appearing, but I'd have to think about, I haven't heard it phrased exactly that way.
So if you want an actual question, my thing is, you know, given a graph and a parameter K such that G is K colorable, what's the fewest number of extra colors I need in my universe to be able to move between any 2 K colorings?
Okay.
So, I mean, clearly this parameter exists because if I just if I give you like N extra colors, then it's dumb.
Right, sure. No.
But I feel like this number should actually be very small. Like maybe even just like 2. Like
I would be I would be interested to think about it. I
Okay.
don't know the answer off the top of my head.
Yeah, fair enough. That's just, I don't know. I think that's a
Yeah.
bit curious.
No, it's I don't know. That's
Fair enough.
what I'll say. Is I don't know.
Fair enough. Any other questions for Dan? Also, Dan, I know you had to get going.
No,
So-
actually, I don't. I had previously had a hard deadline that went away.
Ah,
So I
oh,
don't
okay.
have to get going right away. I have some wiggle room.
Fair enough. Any other questions for Dan?
Yeah, so you use the loaded term mixing, and I'm wondering if there's any sort of random walk issues involved in this, or if you.
I use the term mixing because, in general, questions about are all of the K colorings K equivalent to each other? This, in general, this question absolutely has roots in statistical mechanics, and they want to know. You can create a Markov chain, right? And your Markov chain is all the states or all the K colorings, and then you take a random step, which is pick some valid Kempe swap and do it. And then you can ask questions about what happens with this Markov chain. I don't know any connections to our particular problem here that I'm talking about. It's nice terminology and it makes sense, right? And so I don't know, as far as I know, we are the first people to have really studied this list coloring with Kempe swaps, right? It's sort of, you have to be careful. Initially, it doesn't seem like it would necessarily work, but you can make it work. To a large extent, you can make it work. And so it's a little surprising. So I don't know anybody who's actually studied this in terms of there's a Markov chain, how fast does it mix? What I would say is when you talk about Markov chain mixing, sort of step 0 is to prove that it's actually ergodic, right? Which is that the Markov chain is connected. And it's connected, and that you don't have like stuff where you can only be in a state every so many steps, basically. Those are the two things you have to worry about, is you can move from everything to anything else, and eventually if you pick any state and then the other state and any time step that's big enough away later, there's some non-zero probability you'll go there.
By the way,
so I think it has roots in that. I don't know for here, but I like the term mixing. I think it's evocative and it's very pithy. So I just went with it.
so I do know the answer is yes. So this is used for random samplings of colorings. I believe they call this like Glauber dynamics or something.
Yeah,
like
so
that, but it may be
Glauber
slightly
dynamics-
different. But
Glauber dynamics, I believe, is a little bit different.
Okay.
The model there is that you only recolor a single vertex.
Oh, that's only a single one. Okay.
Right.
But these are oftentimes used to basically say that you can get an approximately uniform sampling of a particular number of colorings in polytime.
Correct. So if your Markov chain mixes rapidly, then for anything that you want to sample, so it holds in a much broader context. Thanks, Chris. Is if you want to sample something and you can't enumerate them all, what you can do is you can build the Markov chain, and if you can prove that the Markov chain mixes rapidly in some polynomial number of steps, then you just take a walk in the Markov chain, and where you stop, that's your random sample. That's your nearly uniform random sample.
So things like this are used all over the place, except especially for, epsilon approximating, counts in polytime. Various Markov chains and probably these walks on Chem swaps also, are pretty rapidly mixing under various conditions and give you uniform distributions, probably.
Right.
Yeah.
Does that speak to your question at all, Ryan?
I think it does, yeah.
Okay, cool.
I can give you some references, Ryan, if you do care about similar things at least.
So I typically, I like to pick on the grad students and make them ask questions. You guys are a little bit in luck because there's too many of you for me to like pick and make each one of you ask a question. But somebody amongst all of you, it's okay. Don't feel bad about asking like a stupid or an overly basic question. It's totally fine.
So okay, I'll ask a question. So these exceptions that we get are basically, the problem is not necessarily with the list coloring, but it doesn't work with just regular colorings in general. Is there any kind of extension of that, or say some way to avoid that kind of redundancy back to the just regular coloring?
Yeah, so I think I understand your question, and if I do, I think the answer is yes. So this K3 box K2, the only bad list assignment for K3 box K2 is when all 6 of the vertices get the same list. And the only thing that goes wrong in that instance is, well, I'll go back. It's here. The only thing that goes wrong is that there's these 2 sets, right? So you can interchange orange and green or orange and blue and so on. And so there's this these 6 colorings here that have these independent sets, and these 6 colorings here that have these independent sets, and you can't get between them. Just in the coloring case, if you require that your list assignments for this particular graph are not all the exact same thing, then stuff mixes. I think that's your question.
Yeah, and then would that also be the case for the complete graph situation?
That is a great question. It's something that I should know the answer to, but I don't. The truth is, for the complete graph, we didn't study it in great detail. The argument wanted a case where there were non-adjacent vertices. And a clique doesn't have non-adjacent vertices. So we just excluded it so that we could just streamline the argument. It's a great question, and it's something that we should probably sit down and work through. My guess is that the answer would be yes, but I don't know. I don't know for sure.
Isn't it just yes by your degeneracy argument?
That's what I would think as well.
Because like find your vertex that has like a color not in a lot of these, and oh no, I guess it's not obvious. Never mind.
It's not obvious because
everyone's list could be contained between a bunch of other people's lists, even if they're
When you have distinct lists, what you will get is you will get a nice instance of this here, right? Where you're going to be able to use that color that's not in his list. And so that's going to show you that a big chunk of this is going to mix, right? But it still is going to take at least a couple more steps to show that in fact everything mixes.
Any last questions for Dan? Oh, let's thank him once more. Thanks, Dan. Okay.